So Naveen Dandu was not he didn't took the course for credit, but he was enthusiastic enough to join this volunteering sessions, and he was curious to trying to apply these skills to problem of his interest. And problem of his interest was to help Jabot in addressing the same problem, but from different angles. So Jabot was focusing on the importance of nuclear degrees of freedom, and Naveen's looked at the role of electronic degrees of freedom, spatial position, form of electrons. Floor is yours.
Thank you.
We are
Thank you, Dr.
15 minutes or even 20 minutes later, but let's keep
Hi
going.
everyone, today I'll be discussing my MATLAB research on a topic called rate of charge transfer between p-doped and n-doped silicon quantum dots. So as you can see in the picture, these are the two silicon quantum dots. One is doped with phosphorus, which is n-doping. The right side figure is where the aluminum is an impurity, and then it introduces p-doping in the quantum dot. So what we are interested in is the charge transfer phenomenon between these two quantum dots when they are placed far apart, like through space, or when they are combined together forming a bond, how the charge transfer rates influence the distance between these two quantum dots. So the main motivation behind this project is the application of those materials into photovoltaic device. As you can see, the photovoltaic devices have comprised of both N-type and P-type semiconductor quantum dots. So if we can think of silicon, impure silicon quantum dots has N-type and P-type. So the main principle lies in the interfacial or the dependency between these two N-type and P-type semiconductors, where they can be bonded together if there is a bond, or if there is a contact between N-type and P-type, or there is a depletion zone between these N-type and P-type. And also monitoring the mechanism of these interfacial charge transfers and their dynamics is very challenging, and that will be addressed in this project. So these are the two quantum dots which are placed through space and through bond, and I will be discussing my main goal is to investigate these reactions and investigate the charge transfer between these two dopants to form a dimer. To achieve this goal, I have used three different approaches in this methodology. The first approach is the atomistic model conversion from a 3D model to a 1D model, where you can see here Hamiltonian of a 3D model was converted into a one-dimensional model to utilize this Hamiltonian, or utilize this potential in our MATLAB code. Once we have figured out to convert this, and then we use this propagation of electron density in space via using this evolution operator technique, where the wave function is multiplied with this potential, and to get one step further, like the past time in the wave function in a past time would then be increased to a present future time using this multiplying with this potential. And then we utilize these initial conditions where the wave function is utilized as a Gaussian wave packet, and to find the probability of electron, we square the wave function, and as we have two quantum dots, each is the electron density of electron, probability density of electron in first quantum dot is the PL of t, and then PRT is the right side quantum dot of the second quantum dot of the time was formed. And the rates of transfer is again we utilize this K as a formula where the difference between the final time probability at final time versus to the initial time over the summation of probability over the entire time. And making use of this kinetic rate constants that are formed, we utilize the Arrhenius equation to determine the activation energy using this Arrhenius plots. Making use of this methodology, we then perform the MATLAB code to simulate the wave packets and found these results. The left side potential energy surfaces correspond to the quantum dots when they are bound together, like bridged quantum dots, versus the quantum dots forming a dimer where they are disconnected. So I would call this one as a bridged dimers versus those as disconnected dimers. As you can see, that potential barrier, the activation barrier for bridged dimers is much less, like 3 electron volts, compared to the activation barrier for disconnected dimers. And I also have the this movies or the electron transfer dissipation from one quantum dot to another in case of bridged dimers versus the disconnected dimers. As you can see, the electron dissipation is much faster or much more contributed towards the right quantum dot in case of bridged dimers versus the disconnected dimers. Thus, we also, as I have shown in the methodology, we tried to calculate this rate constants using the formula, and in this case we used 2 different methodologies as was discussed by my predecessor speakers, where they used the momentum operator in either coordinate space or the position, and I compared both the solid line corresponds to the bridged dimers versus the dotted lines, which is corresponding to the disconnected dimers. As you can see, the rates are much faster for the bridged dimers compared to the disconnected dimers. Here in the second panel, I am showing the time transfer time rates. The time decay is much faster again for the bridged dimers versus the disconnected dimers. As we have the rate constants here, I made use of these rate constants and compared with the temperatures and utilized this Arrhenius equation to plot the Arrhenius graphs, and I found the slopes, from which I calculated the activation energies and found that the activation energy trend is similar to what I found through the potential energy surfaces, that the activation energy is much shorter for bridged dimers compared to the disconnected dimers.
Why do you have 4 lines there on your left side?
In this one, I used two different methodologies. One is the momentum in coordinate space, and one is in the position.
So red
is for in position, the black is for the coordinates. And we are also interested in doing this dynamics calculation of charge transfer, where I utilized 4 different potential energies, initial momentums ranging from 0.1 to 0.4, where the initial momentum is much maximum. The higher initial moment where the electron transfer, it can cross the potential barrier, is where the 0.4 atomic units of initial momentum. The bridged dimers have much higher electron dissipation compared to the disconnected dimers. With this, I would like to conclude with the following conclusions. The charge transfer rate is like about 3 times faster for attached dimers compared to the disconnected dimers. And the disconnected dimers, as they are slower, as they have the slow rate of recombination, because there is a high potential energy barrier, and because of this, it can be used in photovoltaic devices, and they can be connected to the metal bias as gold. And this recombination of charge transfer rates, if they are fast, that's bad for the photovoltaic devices. That's because of this, there should not be any. We should avoid this, or we should slow down this charge transfer phenomenon between p-doped and n-doped conductors, semiconductors. And if we also consider nuclear reorganizations, as Javed was doing, if I consider those in my calculations, the rate of charge transfers will be much slowed down further compared to the values I was showing here. With this, I would like to thank Kapil because of for his constant support and unconditional reviews on this paper. Thank you very much, and then thanks to you, fellow audience.
Okay.